Hello, everyone. I think we're going to go ahead and get started. Hey, my name is Mihir. I guess that's Brian. And today we're going to talk a little bit about training MoEs at scale with PyTorch. So let's get started. I really like this tweet by Andrei Karpathy. I think it captures a lot of the challenges of training large models at scale. So normally when you're training a model, it's pretty simple. You can just use PyTorch and things mostly work. But as you scale, you start to see a lot of complexities and failures in weird parts of the system, from hardware failures to challenges in determinism to things like S3 going down because your model checkpoints are too large. This talk is meant to highlight, I guess, some of the painful learnings we've done from going through this process. So I guess a little background, Brian and I work at Mosaic as part of Databricks, and at Databricks we help build a platform to train large AI models at scale, where we sort of build out a lot of the infrastructure and make it so that it's really easy for you and you don't have to worry about these set of problems. In this talk, we're going to sort of be talking about rows 3 and 4. So essentially, how do we use PyTorch and work with the PyTorch distributed team to train at scale?
So we'll first start off with an intro on what is MoE. But before we get into what an MoE is, I'll briefly go over LLMs and transformers. An LLM essentially is you have an embedding layer, you have transformer blocks that are all stacked on top of each other, and then you have some decoding layer. So your input goes in through this embedding layer, then it goes through each transformer block, and then you send it to your own embedding layer that will calculate some softmax over which token is most likely to be next output. Diving deeper into the transformer block, you have two parts. The first part is the attention block, which essentially tells you what parts of your sentence are most relevant to some particular word. And then you have your feed-forward network. The feed-forward network is traditionally implemented as some multi-layer perceptron layer, but there's been research into other types of network you can use for that. When you're looking at a MoE specifically, you're taking that feed-forward network and breaking it down into multiple expert networks. These can be smaller feed-forward networks, or they can be several glue blocks, as you see in the picture there. But you have a router that comes before these expert networks that will take in a token and determine which experts to send that token to, and will also combine the output of the experts at the end. This replaces the traditional feed-forward network in your transformer block. So why do you want to use an MoE? There's benefits on the training side and also benefits on the inference side. On the training side, you're able to do more efficient training for some given flop budget. This is because for a particular token, only a subset of your experts are seeing that token. So you're able to process more tokens for some compute budget. Now, once you have an MoE trained, you're also able to get benefits when doing inference. You have faster inference compared to a dense model because similarly during training, token is only routed to a subset of experts. So you only need to do a small amount of computation for a given token. There's different design choices that come with MoEs too, like how many experts you should have, or how many experts you should route a token to, known as top K, that are design considerations you need to take into account when balancing training and inference trade-offs. The particular MoE implementation we use is called MegaBlocks. So MegaBlocks is an open source library that allows for sending a variable number of tokens per expert. Previously, different MoE implementations assume you have some fixed capacity per expert. So maybe an expert can only take in 4 tokens. If the router routes additional tokens to that expert, then you need to drop tokens because they exceed your capacity. Or if your router only routes, let's say, 2 tokens to an expert that has 4 capacity, then you need to pad your tokens to 4, and that wastes computation and memory. So the graphic shows like you'll have fixed size experts and you'll have these sparse block matrix multiplications when you have a variable number of tokens.
Cool. So it's a quick primer on MoEs. As many of you probably know, there's a lot of cool MoEs out there like Mixtral and DeepSeek, and we think it's a very popular area where more and more people are willing to train these models. So now we're just saying, okay, I know what an MoE model is. How can I train it efficiently at scale? And to that, we're going to talk a little bit about different ways of parallelizing large models and how we specify that for MoEs. So as a brief background context, let's talk about different forms of parallelism. Let's say you're training a model and I have one GPU. It's pretty easy. The model goes on the GPU and I give it some data, compute some gradients and updates. Now if I'm extending to multiple GPUs, I can do something called data parallelism. So PyTorch has this really nice API called DDP, Distributed Data Parallelism, which basically says you put a copy of the entire model on every GPU, and every GPU gets a different batch of data. And with that batch of data, you're going to compute a set of gradients that are communicated across all of your devices and reduced. The extension to this is FSDP, which is fully sharded data parallelism. So as your model gets really big, it might not fit on a single GPU, and you need some better way of parallelizing it. So what FSDP does is it says, let's take a model and shard it. So instead of every GPU having the entire model, every GPU only has a piece of the model. Then when you need to do any computation with that model, you're going to gather that part of the model. So as a quick example, let's say I'm doing a forward and a backward pass on a single layer. I'm going to load the sharded model, and then I'm going to say, okay, I want to do a forward pass. Let's say it's like the first FFN. At this point, I'm going to do an all gather, which is the second column in this diagram, and gather that layer only. I'll then do all my computation, and then I'll free all the memory. And I'll do the same thing in my backwards pass. Before I do the backwards pass for that layer, I'm going to gather that layer, do the backwards pass, and then update the gradients. So this is really great and is what I'd say is sort of the default way of training large models up till a handful of thousands of GPUs. And we get pretty good performance with this. But for MoEs, we can actually do a little bit better. So one of the challenges with MoEs is your parameter counts are actually a lot larger than your corresponding standard dense transformer. That's because instead of having one FFN, you have multiple copies of these. You have multiple experts. So to do this, there's a lot of interesting work in literature around this idea called expert parallelism. So let's go through like a simple 2 GPU example. Instead of saying I'm going to replicate the entire model on every GPU, like we do with data parallelism, I'm instead going to split up the model across multiple GPUs, closer to something like tensor parallelism. So this example, we're going to put expert 1 on GPU 1, and we're going to put expert 2 on GPU 2. Now, when I get some data on either GPU, I have to figure out, okay, this data, based on the router, wants to go to this expert. So if I look at the orange block on GPU 1, this orange block is saying, okay, some data that's being routed to expert 2, so I need to communicate that to GPU 2, where it's going to do the math, and then it's going to send it back to GPU 1. As another example, on the red block next to it, well, this time the data was routed to expert 1, and since expert 1 is already on that GPU, I don't have to do any additional communication. I can keep it on the same GPU. So why would I want to do this? It's definitely adding a lot more complexity. And the short answer is it makes higher MFU. So MFU, for those of you who are not familiar with it, is called model flop utilization. And you can think of this roughly as how effectively am I using my accelerator. So let's think of like a single H100. If I'm doing BF16 math on H100, I get about 1,000 teraflops of math per second. And I want to say, let's make sure my code is getting as much math possible out of that GPU. So a good dense transformer might get something like, let's say 450 teraflops. You're getting roughly 45% MFU. And when you're training a large model, you want to say, I want that MFU number as high as possible because that decreases my cost, decreases my training time, et cetera. And essentially what happens with expert parallelism is you get higher MFU. The short answer for why is basically by routing the data to one copy of an expert across the node, you get larger matrix multiplications. So instead of doing, let's say like in this case, 2 matrix multiplications per GPU per expert, I now am only doing 2 matrix multiplications in total across all the GPUs. And so by doing fewer matrix multiplications that are larger, I get better utilization of my GPU. This is roughly because larger matrix multiplications are more efficient on hardware. If you're curious why, there's this really great blog by Horace He on what makes matrix multiplications fast on GPUs. Okay, so this works really well for my training performance, but it makes my setup much more complicated. Now I have GPUs that are no longer homogeneous, and there's much more complicated design in the parallelism. Okay, so in practice, we've introduced this new idea of expert parallelism, but expert parallelism alone is not sufficient. I sort of want to combine it with FSDP to scale to thousands of GPUs. And the way we do this is through this really cool API called device mesh, which PyTorch introduced in 2.2 and is now really, really solid and reliable as of like 2.4. So to explain what device mesh is, we can sort of look at our parallelism across all the GPUs. And we see that what we're here doing is, in this example, we have 32 experts and 8 GPUs per node. And I'm spreading out the experts across all the GPUs. So I have 4 experts on each GPU going in a row. And then on the vertical dimension, I'm saying take the experts on that GPU and shard it vertically. So that's where the FSDP sharding is coming from. And instead of sort of thinking about these things in local sharding and replicate operations, I can instead view this as a mesh. So I'm basically defining a 2-dimensional mesh across all of my GPUs. And I'm saying one dimension is the expert shard dimension, one dimension is the FSDP shard dimension. And in general, PyTorch lets you sort of define any arbitrary n-dimensional mesh of shards and replicates. So this makes it super, super easy to describe my layout. I can say, here's my model on one GPU. Here's my sharding pattern. When I want to checkpoint, I just say, gather across all of the shard dimensions. And I get a very nice, clean, single checkpoint. Okay, so that works up until roughly 512 GPUs. And then things get a little bit more complicated. So as you want to scale to thousands of GPUs, one thing you'll notice is there's a lot of communications we're doing with these sharding. When you do FSDP, you're gathering across the shard dimension. You can think somewhat intuitively, when I have more GPUs participating in a communication operation, it's slower. There's a greater chance of a single GPU being a straggler. There's more hops I have to go through in the networking. And we basically just want to avoid our communication collectives becoming too large. So you can roughly measure this as sort of like what is the communication bandwidth ratio, bandwidth rate. And you can see this decays pretty quickly as you increase the number of GPUs. So to avoid this, we introduced this thing called HSDP. So it's called hybrid sharded data parallelism. Now, in the left example, you can think of this as normal FSDP, where every block is a node of 8 GPUs. And we're sort of sharding across the entire cluster. So this is roughly like a 512 GPU cluster if there's roughly 16 nodes and each node is 8 GPUs. Sorry, 128. Now, instead of doing that, I can do something like HSDP, where I'm now sharding in smaller blocks. So now I'm saying only shard in blocks of size 4. Only shard in blocks of size 4. So now I'm saying only shard across 32 GPUs, and then replicate across these blocks of 32 GPUs closer to what DDP does. So this is really great because now I sort of have all of my communication collectives across smaller sets of GPUs. I have a shard across 32 GPUs, and then I have a replicate across 4 sets of GPUs. And this basically just means all my communications operations are much faster, and I get, again, better performance. So if we go back to the device mesh abstraction, you can think of this as saying we're now adding a 3rd dimension to the abstraction. This is now a replicate dimension, and so now you have a 3D device mesh. And it would have been cool if I could have figured that out, but I couldn't figure out how to cleanly draw a 3D device mesh. So we get a 1D view.
So Mihir has talked about how do we scale to thousands of GPUs and how do we do training efficiently, but the real world isn't perfect and you're going to have to deal with failure modes. And one of the most common failure modes is GPU dies or like node goes down. And as you scale to more and more nodes, this becomes increasingly frequent. So the way to get around this is model checkpointing. That's basically just during like a model training run, you're saving the state of your model at time intervals, and so that if your training run fails or dies, you'll resume from training at the latest checkpoint instead of having to start your training over from scratch. So there's 2 concepts I'm going to talk about. First is sharded checkpointing, and the second is elastic checkpointing. So sharded checkpointing is what it sounds like. When you shard your model over many different GPUs, instead of having to checkpoint by gathering the entire model onto one GPU and saving a full copy of that model from that one GPU, instead you have each GPU save the portion of the model that's been sharded to it. So that's the first two boxes in the figure. Let's assume you have two GPUs and you're saving a checkpoint. So GPU 1 uploads the first shard to its object store, and then GPU 2 uploads its own shard to the object store. Then we go on to elastic checkpointing. In this case, elasticity means you can vary the number of GPUs you're resuming on compared to what you saved on. Commonly, this is because, let's say you start off with a cluster of 1,000 GPUs, you have a couple nodes die, and now you're suddenly left with 900 GPUs. So you need to be able to keep training on those 900 GPUs and not have to wait for 100 more GPUs to come online before you can resume your training. And this comes in through PyTorch's distributed checkpointing library, where they're able to calculate, based on the shard metadata, which GPU that you're resuming on should read from which shard. So in our simple example, we have 4 GPUs. That means we're sharding our model into fourths over these 4 GPUs. Let's assume shard 1 contains the first half of the model based on GPU 1 in the original run. So your GPU 1 is now just taking half of shard 1 and loading that model, and then GPU 2 is taking the second half of shard 2. Similarly for shard 2 and then GPU 3 and 4. So both these features are implemented in PyTorch's distributed checkpointing library, and they provide nice APIs to do all this calculation under the hood of if I have different number of GPUs, like how do I know which shard contains what data that I need to load in. Going beyond like hundreds of GPUs, you also start running into network issues. So we used S3 for our big model training run, and we're trying to download tens of terabytes of data on resumption. And this caused S3 to start bottlenecking us and timing us out because we're just trying to load too much data in too short of a time. But you don't want to slow down like the rate of your requests because then your resumption is going to take too long. So Mihir previously talked about HSDP, and he talked about how each replica essentially contains the whole model. And our workaround for this was, instead of saving all our models, instead of saving multiple shards from each replica, because one replica already contains the whole model, you can just use that replica to upload and to download. So you'll have replica 0 save the model, and then on resumption, you'll also only download on replica 0. And to get the model to all the other replicas, you take advantage of like InfiniBand and broadcast your model weights to the other replicas. This allows you to start training after a failure in under 5 minutes. So everything we've talked about in this talk is open source repos. Obviously, we've built on top of PyTorch. We have Composer, which is our training library using PyTorch. And then we have a separate library called LLM Foundry that contains the code and model definitions for LLM training. We've also talked about MegaBlocks for MoE-specific layers. And if you guys have any questions, our contact information is below.